Hey guys, welcome to topic 13. This topic is all about geologic history. All right, so we're going to be interpreting the past using different methods. All right, so first off, I want to start out with this example called dendrology. It's a study of tree rings. Okay, and this alone is an example of something obviously more recent studies we can figure out about the climate of the past. So you look at the tree rings. Thicker tree rings indicate a warmer growing season, whereas a thinner tree ring indicates a colder growing season. So you can figure that out and tell a lot about the climate of the past. Okay, so obviously more recently, because these trees were only alive the last hundreds of years at most. All right, but either way, we're also going to look at really old stuff on Earth, going back to Pangea time and even further, all right, to the beginning of the Earth, using, of course, fossil evidence. So let's take a look how we do that and the methods on how we interpret the past. So first thing is looking at the age of rock layers. We do it with something called relative dating. Okay, so relative dating is actually putting rock or geologic events in chronological order. What came first, second, third. And we usually start from the bottom, which is the oldest, and work our way to the surface, which is the youngest. Right? That's the best technique to kind of go through the order. All right, and obviously that's the simplest thing that happens. Oldest on the bottom, youngest on top. That's not always going to be the case, though. Okay. We could also use artifacts within the rock material, whether it be living things or formerly living things, fossilized, or it could be obviously in this is a more recent example. It's got skulls, bricks, and different things from people living in that area. Okay, so that's an example of you can use relative dating also. And the reason why it's called relative is because it's a comparison, all right? There's no exact age you're getting out of this. It's just a comparison to what's around it. All right, to get a more accurate answer, we can do something called absolute dating. So absolute dating is finding the actual age of the rock or geologic event in years, okay? And what we look at is radioactive material within the substance as it breaks down. So what happens, there's something called radioactive isotopes. These things will break down at a predictable rate, and we look at the percentages of what's left over, so what has decayed and what is still radioactive, and we're able to figure out the age of the rock. Okay, and then we give names to these time periods based on the type of fossils that are present. So Devonian, Mississippian, Pennsylvanian. So that's going to be the center part of the reference table, page 8 and 9. You're going to see those geologic periods that are listed. Okay, and we have how many million years they last. There's no set time for those. It's basically based on fossil evidence. All right, so trilobite, an example of a fossil that existed a long time ago. All right, and we can combine the two. When you combine the two, you get a little more of an answer. So relative dating could be used first, and then we could use fossil evidence to solidify what the age of the layers are. We can even date something like volcanic ash, looking at volcanic eruptions, because some of these actually can be game changers in the world, of course. So we'll talk more about that, catastrophic events that happen on the Earth's surface. Okay, definitely one thing you have to do is assume a couple things because we're dealing with stuff that is a long, long time ago. All right, when you look at existence, we're only less than 1% of existence. Okay, so with each of these methods, geologists rely on one important assumption of the past, which is the principle of uniformity, which says the present is the key to the past. All right, so in other words, by looking at what we know now, all right, so understanding the geologic processes that are happening today, we can better understand what happened in the past, all right, because we got to piece this whole thing together And only way we can do that is understand what happens now better, to relate it to the past. Okay, so erosion, deposition, plate tectonics, all things we figured out. By looking at these characteristics of rocks, geologists can make conclusions about the past. So we use what we know now to understand the past much better. Okay, we also do something called correlation. Correlation is putting in age order, all right? So we might do this between rock layers of different locations, all right? So we'll be doing that in this chapter. It's almost like puzzling, doing a puzzle almost. So people that like doing that will enjoy this, putting it in age order. Just remember that types of rocks can show up multiple times, so we'll look at that. So you have to use other clues to figure out the age. So correlation is a matching of the age of the rocks, geologic events in different places based on the characteristic of the rocks. And there's 4 ways we can do this. So the first thing is simply just walking the outcrop. So an outcrop is basically a section of bedrock that's been exposed at the Earth's surface. So if the rock formation is exposed, an individual can follow the outcrop from one place to another. All right, perfect example of this is if you're driving up the roadways, especially upstate New York, Pennsylvania, different surrounding states, you'll see exposed bedrock on the side of the road. Okay, you can follow that from one place to the other and reconstruct the past. All right, and I've done this in past field trips in some of my geology classes. All right, but that's definitely something you can do to figure out age of rocks. Okay, and most outcrops are not exposed for large distances. The only reason ours are along the roadways are because they dynamite blasted to open up for the roadways. Okay, so a lot of times you'll see that danger falling rocks. That's the reason why, because that area has been dynamite blasted once before, and it can become unstable and collapse due to the, you guys know, erosion that happens. Okay, so here's an example of one, and you can see the rock layers are not horizontal anymore, so obviously crustal movements have happened, and this is actually a fold, right? You can see the shape of the fold, all right, on both sides. So the oldest rock layers are right here in the middle, and then the youngest probably are out here, right, which continues to fold all the way out here. Okay, similarities of rocks. So rock formations separated could be correlated based on their appearance, like I mentioned already. Okay, the only problem is that 2 different rock formations of different ages could have the same characteristics. So you got to be careful. Use the surrounding rock layers also in your clues to figure out the age compared. All right, this is really important in this chapter, index fossils. Okay, so index fossils is so in general, a fossil is any evidence of past life. It could be burrow holes, excrement, it could be bones found in the rock. Okay, so any of those things, anything related to that creature being alive on the earth. Okay, index fossil is a fossil that has to meet 2 criteria. Okay, number 1, they have to live over a large geographic area. So they have horizontal distribution, that's one way to say it. They're found all over the world. Okay, so found on many continents will actually be a good index fossil. They also live for a short period of time. They have vertical distribution. So in other words, they're only found in one rock layer. Okay, because if they're in multiple rock layers up a sequence of rocks, the problem with that is it's been living for too long to be considered an index fossil. Index fossil are a marker for time. So basically being alive for a short period of time. Short period is still millions of years, geologically speaking, but in general it will only be in one layer, found in multiple areas. Okay. So here's an example of that. These are index fossils being matched up. You can see 3 and 3 match up because they have the same index fossil. Okay, these are underneath, so these have to be the oldest. Okay, 4 and 4 match up. 5 disappeared from this assemblage, but 6 is still here. So what happens, you can see this wavy line here. This indicates this layer got eroded away. All right, so number 5 got eroded away sometime in geologic history. All right, and then 7, 8 were deposition put down here by deposition, but maybe not in this location. Okay, so sometimes you're going to have incomplete assemblages, so you guys got to kind of figure it out, piece it together, and figure out the age compared to each other. Okay, and lastly, I want to end with volcanic ash, very small rock fragments, volcanic glass that are released from a volcano as a dust cloud. Okay, this ash actually spreads over thousands of kilometers, even around the whole world sometimes, by the wind before settling. So, good thing about this, just like your index fossils, it will be compacted into rock. Each volcanic ash has a specific mineral composition. You can actually pinpoint it towards that volcano. And it's useful because volcanic ash can actually take a period of time to settle, only days, weeks, which means the volcano will be a mineral fingerprint useful in correlation. All right, so it can be used in age descriptions, age comparisons also, just like an index fossil. All right, because it's spread out in a short period of time, and it's one little thin layer in the world. So here's an example of one. You can see big dust cloud goes up. That will settle all over the Earth's surface, and you can see the remnants of it. That will compact into a rock eventually. That's the ash. So volcanic ash, just to give you an idea, Mount St. Helens, 1980, enough ash fell to cover a football field, so 100 yards, 150 miles deep. Okay, so that's an incredible amount of ash, and it circled the globe in less than 3 weeks. So either way, these small little particles, they'll make a thin layer on the Earth's surface. It's a good marker of time, so you could figure out age relative of different rock layers. Okay, and that's it for beginning of geologic history. All right, so we'll go more into detail about each of these. Thanks for tuning in, guys.